What if I told you that the most iconic dinosaur in history was actually a scientific lie? For more than 100 years, paleontologists, museums, and filmmakers showed us a T-Rex that couldn't have survived a day in the real Cretaceous world. The evidence was right there in the fossils, but early scientists made critical errors in their reconstructions that completely misrepresented this apex predator. Today, biomechanics and 3D modeling have finally corrected these century-old mistakes, revealing a dinosaur so different from what we thought we knew.
For over a century, every museum display, every textbook illustration, and every Hollywood movie got the world's most famous dinosaur completely wrong. The Tyrannosaurus Rex you grew up seeing, standing upright like a kangaroo, dragging its massive tail behind it with those tiny, seemingly useless arms, never actually existed. Scientists built this image from incomplete fossils and outdated assumptions, creating a monster that was more fiction than fact. But modern technology has finally revealed the truth about this apex predator, and it's far more terrifying than anyone imagined. The absence of tail drag marks in ancient sediments and sophisticated 3D modeling studies would eventually expose just how fundamentally wrong this iconic image really was. The story of this scientific revolution begins with a single decision made over a century ago. In 1905, Henry Fairfield Osborn made a decision that would shape how the world saw dinosaurs for the next 100 years. Working with fragments of bone discovered by Barnum Brown in the Badlands of Wyoming, Osborn officially named the species Tyrannosaurus rex, meaning Tyrant Lizard King. But Osborn faced an enormous challenge. He had to create a complete picture of this ancient predator from incomplete remains, and the pressure to display something spectacular in museums was intense. The fossil evidence available to Osborn and his contemporaries was frustratingly limited. The holotype specimen catalogued as CM9380 provided only about 13% of the complete skeleton. Missing were crucial pieces of the puzzle, complete hip structures, full leg assemblies, and clear evidence of how these massive bones actually connected in life. Victorian-era scientists had to fill these gaps somehow, and they turned to what they knew best: modern animals. Osborn and other paleontologists of his era looked at large reptiles like iguanas and made what seemed like logical comparisons. They observed how these creatures stood upright on their hind legs when threatened or feeding, and assumed that a massive predator like T-Rex must have adopted a similar stance permanently. Without complete hip joints to show the actual articulation, the thinking was straightforward. Larger animals needed to stand more vertically to support their weight, just like kangaroos or bears rearing up on their hind legs. This reasoning reflected the broader scientific thinking of the Victorian period, which often portrayed dinosaurs as primitive, inferior creatures that represented evolutionary dead ends. The image of a lumbering, upright giant dragging its tail matched perfectly with the era's view of dinosaurs as sluggish reptilian failures unable to compete with the superior mammals that eventually replaced them. When Osborn's team mounted the first T-Rex skeleton at the American Museum of Natural History, they created more than just a museum display. They established a template that would be copied in institutions worldwide for decades. This single reconstruction became the definitive image of T-Rex, appearing in textbooks, educational materials, and eventually Hollywood movies. The cascade effect was remarkable. One interpretation based on incomplete evidence became scientific gospel. Yet decades later, when scientists like Sue Hendrickson discovered specimens reaching roughly 80% completeness, the fossil record itself would reveal that researchers had been overlooking the most obvious evidence of all. The breakthrough came when scientists realized they had been staring at the most obvious clue for decades without seeing it. T-Rex's massive tail, which made up nearly half of its total body length, held the key to understanding everything wrong with the traditional reconstruction. For generations, paleontologists had assumed this enormous appendage simply dragged behind the creature like a reptilian anchor, leaving deep grooves in the ancient mud wherever these giants walked. The tail-dragging theory seemed logical enough that scientists even calculated the evidence it should have left behind. A creature weighing 6 to 9 tons, dragging a tail several feet in diameter, would have carved unmistakable furrows through Cretaceous sediments. These grooves should have been preserved in the fossil record alongside the famous three-toed footprints that T-Rex left behind. But when paleontologists examined trackways from the Hell Creek Formation and other T. rex habitats, they found something that didn't make sense. The tail drag marks were completely absent. Despite examining over 100 track sites across Hell Creek Formation deposits, not a single trackway showed evidence of a dragging tail, even though these same sites preserved intricate details of footprints, including individual toe impressions and skin texture patterns. This absence created a scientific mystery that demanded explanation. If T. rex wasn't dragging its tail, what was it doing with this massive structure? The answer came through biomechanical analysis that revealed the tail's true function as a sophisticated counterbalance system. Scientists studying the vertebral structure discovered intricate muscle attachments and ligament connections that transformed the tail into a dynamic stabilizing mechanism. The caudal interspinous ligaments acted like biological springs, storing and releasing elastic energy with each step. The natural frequency method studies took this understanding even further. Researchers constructed detailed biomechanical models using adult specimen RGM, HARD 2000, known as TRIX, and discovered that the tail's oscillations matched T. rex's walking rhythm perfectly. The tail's natural frequency of 0.66 seconds, roughly one side-to-side wag every 2 seconds, corresponded to an optimal step frequency that maximized energy efficiency during locomotion. This meant T. rex could maintain its preferred walking speed of 4.2 feet per second, about 3 miles per hour, with minimal energy expenditure. This discovery triggered a complete re-evaluation of theropod locomotion. The creature moved with a horizontal posture, head forward, body parallel to the ground. But the implications of this athletic reconstruction extended far beyond simple posture correction into realms that would challenge everything scientists thought they knew about this predator's capabilities. The athletic reconstruction revealed sensory capabilities that transformed T. rex from lumbering giant into precision predator. What researchers found next would shatter every assumption about this creature's intelligence and hunting prowess. Modern apex predators like lions and eagles would seem nearly blind compared to the sensory arsenal that T. rex possessed. The popular image of a dim-witted brute stumbling through prehistoric forests couldn't have been further from the truth. Those grapefruit-sized eyes weren't just for show. They housed visual systems that put modern raptors to shame. While Hollywood movies like Jurassic Park claimed T. rex had poor vision and couldn't see stationary objects, the fossil evidence tells a completely different story. Scientists analyzing skull structure and eye socket dimensions as documented in Nature and JS daily studies discovered that T. rex could see with 5 times the precision of a falcon and 13 times better than humans. This visual acuity meant spotting a deer-sized animal from over a mile away was well within its capabilities. The sophistication extended far beyond simple sharpness. Studies published in JS Daily revealed that T. rex possessed advanced color vision with superior color discrimination and ultraviolet detection capabilities. Like modern birds and crocodiles, this apex predator could perceive ultraviolet light and distinguish color variations across a spectrum beyond human perception. Camouflage strategies that might fool other predators would have been significantly less effective against T. rex. Every subtle color variation in hide patterns, every attempt at blending into vegetation, would have been far more visible to these hypersensitive visual systems. The forward-facing placement of those massive eyes created something even more deadly. This arrangement provided exceptional depth perception, as evidenced by the forward-facing orbits and enlarged brain regions devoted to vision described in Royal Society studies. Brain endocast analyses revealed enlarged regions dedicated specifically to processing this constant flood of visual information. The skull's internal structure showed development patterns similar to modern raptors, with significant neural real estate devoted to integrating sensory data. The olfactory regions were equally impressive, with genetic studies suggesting T. rex possessed almost as many genes encoding smell receptors as house cats. This combination meant T. rex could track prey through multiple sensory channels simultaneously. Every aspect of its skull architecture pointed to one conclusion: this was a precision killing machine built for tracking, pursuing, and eliminating large prey with ruthless efficiency. Yet even with these revolutionary discoveries, paleontologists continue wrestling with fundamental questions about T. rex anatomy that remain hotly contested today. The most heated debates among paleontologists today center on those infamous tiny arms that have puzzled scientists for over a century. Stephen Stanley from the University of Hawaii in Manoa champions what he calls the vicious slashing hypothesis, arguing that these seemingly inadequate limbs were actually precision weapons designed for close-quarters combat. Stanley points to the unusual joint structure that allowed movement in multiple directions, combined with 4-inch-long claws that could deliver devastating strikes to struggling prey. But not everyone agrees with Stanley's slashing theory. Jacob Vinther from the University of Bristol favors a more conservative interpretation, suggesting the arms served a minor subsidiary purpose, like clasping during mating behaviors. Thomas Holtz, a tyrannosaur expert at the University of Maryland, raises practical concerns about the slashing hypothesis. He argues that the arm's short reach would have forced T. rex to press its chest against victims to use them, effectively preventing the predator from deploying its most powerful weapon, those bone-crushing jaws. The evidence behind these debates reveals remarkable complexity. Despite their small size relative to the body muscle reconstruction studies, demonstrate that T-Rex arms possessed robust musculature capable of significant strength. Stress fractures found in fossil arm bones by Rothschild and Molnar indicate repeated loading during the creature's lifetime, though whether this supports slashing attacks or other functions remains contested. The injuries discovered in shoulder regions suggest these arms experienced substantial forces, possibly from holding on to struggling prey during attacks. The Nanotyrannus controversy adds another layer of complexity to these discussions. Scientists continue debating whether Nanotyrannus lancensis represents a distinct species or juvenile T-Rex specimens. This classification dispute matters because juvenile tyrannosaurs may have used their proportionally larger arms differently than adults. Holtz notes that younger individuals had larger strike zones relative to their body size, suggesting arm function changed throughout development. The feather evidence debate represents another ongoing controversy. While relatives like Eutyrannus huali possessed feathers, skin impressions from the Y-Rex specimen show scales rather than feathers. Evidence from Dilong and other feathered tyrannosaur relatives suggests complex integument patterns that may have varied across body regions and life stages, leaving questions about juvenile plumage and arm covering unanswered. These debates demonstrate how every new fossil discovery forces scientists to reconsider fundamental assumptions about T-Rex anatomy and behavior. What we consider definitive knowledge about this apex predator continues evolving as researchers challenge established interpretations with fresh evidence. The scientific method demands this kind of rigorous revision. The century-long transformation of T-Rex represents science at its finest, with researchers abandoning deeply entrenched beliefs about this apex predator when evidence demanded change. The shift from upright kangaroo-like posture to dynamic horizontal hunter demonstrates how scientific understanding evolves through constant questioning and testing, even when it means overturning fundamental assumptions. This ongoing revolution should make us wonder what other prehistoric facts might be completely wrong. Future discoveries about arm function, growth patterns, and sensory capabilities continue reshaping our knowledge. New juvenile specimens and advanced biomechanical models will undoubtedly drive further revisions, keeping T-Rex research dynamic and ensuring continuous inquiry into this apex predator's true nature. The T-Rex our grandchildren study may differ as dramatically from today's version as ours does from that tail-dragging museum giant of the past.
For decades, we've been told that Spinosaurus was essentially a giant crocodile with a sail on its back, spending almost all of its time underwater hunting fish. This image became so popular that it dominated documentaries, museum displays, and even Hollywood movies. But what if I told you that this entire narrative is crumbling? Recent fossil discoveries are revealing something far more interesting about this 50-foot predator. The evidence suggests that Spinosaurus wasn't the aquatic specialist we thought it was, but rather something much more versatile and terrifying.
You've probably seen the documentaries showing images of Spinosaurus wading and partly submerged in ancient rivers like some massive aquatic predator. I used to believe this too until I started examining the actual fossil evidence. What I found was surprising While Spinosaurus had amazing adaptations for fishing and swimming, it also retained crucial features for life on land. The more I learned, the more I realized we've been looking at this predator all wrong. It wasn't just a swimmer, it was something far more versatile and dangerous. For decades, paleontologists have debated what kind of lifestyle this massive predator actually lived. The discoveries between 2014 and 2020 seemed to settle the argument once and for all, painting Spinosaurus as a semi-aquatic predator. But bone density studies and inland fossil occurrences reveal a different story entirely about how this transformation in thinking actually began. The transformation of Spinosaurus from land predator to aquatic giant began with a single fossil discovery that would reshape everything we thought we knew about this massive dinosaur. In 2014, paleontologist Nizar Ibrahim and his team announced they had found remains of Spinosaurus in the Kem beds of Morocco, and these bones told a story that nobody expected. The femur was shorter than anticipated, suggesting reduced reliance on walking. The bones themselves were unusually dense, a characteristic typically found in animals that spend significant time underwater. These dense bones, known as pachyostosis, immediately caught the attention of researchers worldwide. Studies comparing Spinosaurus limb bones to water-dwelling animals like penguins, as detailed in the Nature 2022 paper on bone density in aquatic pursuits, showed similar structural patterns. When Ibrahim's team analyzed the Spinosaurus bones under microscopes, they found the same characteristics that help modern hippos and manatees control their buoyancy while submerged. The implications seemed clear. This was a dinosaur built for life in the water, not on land. The real game changer came in 2020 when researchers uncovered the first complete tail of Spinosaurus. This wasn't just any tail, it was a massive laterally flattened structure that looked remarkably similar to the tails of modern crocodiles and marine reptiles. The vertebrae were elongated and supported by tall neural spines, creating a paddle-like appendage that measured over 20 feet in length. However, analyses by Frank Fish et al. In eLife 2022 showed the tail generated limited thrust of less than 15 to 74 pounds force and achieved slow surface speeds of only 2.6 feet per second, indicating Spinosaurus was an awkward swimmer rather than a marine pursuit predator. While Ibrahim et al. Proposed robust swimming adaptations, they did not demonstrate routine deep-water pursuit or full submergence. Scientists began reconstructing the lifestyle of this predator based on these aquatic adaptations. The elongated snout packed with conical teeth seemed perfectly designed for catching slippery fish. The nostrils were positioned high on the skull, allowing Spinosaurus to breathe while most of its head remained submerged. Even the sail on its back started making sense in an aquatic context, possibly serving as a dorsal fin for stability or display while swimming. Research teams compared bone isotope ratios from Spinosaurus teeth to those of other dinosaurs and modern animals. The isotope studies by Amiot et al. In 2010 suggested semi-aquatic lifestyles, but did not fully confirm diet solely from aquatic sources, leaving room for interpretation about feeding habits. Museums around the world began updating their Spinosaurus displays to reflect this new understanding. The old reconstructions showing a bipedal land predator were replaced with exhibits depicting a semi-aquatic dinosaur. Popular documentaries and books followed suit, presenting Spinosaurus as nature's answer to a prehistoric crocodile. The swimming dinosaur narrative gained support when researchers examined the geological context of Spinosaurus fossils. The Kem beds represented a braided river system, rich in fish fossils, though it also contained inland deposits that complicated the purely aquatic narrative. By 2020, the scientific consensus seemed settled around Spinosaurus as a swimming specialist. However, this focus on aquatic features meant researchers were overlooking something important about this predator's anatomy. Beneath the surface of all this aquatic excitement lay anatomical evidence that told a different story entirely. The femur that seemed so short compared to other theropods was actually thick and heavily muscled, designed to support enormous weight. When paleontologists reassembled the complete leg bones, they discovered that Spinosaurus possessed what Sereno et al. Demonstrated in eLife 2022, a bipedal center of gravity positioned over its hips, supporting efficient land locomotion. CT-based flesh models that reconstructed pelvis and hind limb musculature revealed a strong bipedal stance rather than the weak vestigial limbs of an animal that abandoned land entirely. The muscle attachment sites on the femur and tibia tell a fascinating story. Deep grooves and ridges mark where massive leg muscles once connected, indicating that Spinosaurus retained significant locomotive power on solid ground. Modern crocodiles, despite being excellent swimmers, can still gallop at impressive speeds when necessary. The bone structure of Spinosaurus suggests similar capabilities with leg proportions that could easily support its estimated 33,000-pound body weight during terrestrial movement. Researchers examining the foot bones found additional surprises. The pedal phalanges lacked webbing evidence as noted in Chicago News 2022, and instead resembled other theropods, implying they were designed for terrestrial traction. The metatarsals were broad and robust, creating a stable platform for walking on various surfaces. Unlike purely aquatic animals that develop webbed or paddle-like feet, Spinosaurus maintained distinct clawed digits that would have provided excellent grip on muddy riverbanks and sandy substrates. The claws themselves were curved and sharp, perfect for gripping terrain, but also useful for grasping prey or climbing over obstacles. The pelvic structure reveals even more about terrestrial capabilities. The ilium was massive and well-developed, providing attachment points for the powerful muscles needed to move such a large predator across land. The hip socket was deep and well-formed, indicating that the leg could rotate through a full range of motion. This anatomical design wouldn't make sense for an animal that spent its entire life floating in water. Biomechanical analyses of the leg bones show that Spinosaurus could generate substantial forward thrust while walking. Modeled stride lengths suggest it could traverse riverbanks, efficiently covering significant distances without difficulty. This was not an animal confined to the immediate vicinity of water sources. The vertebral column provides additional evidence for terrestrial strength. The neural spines that supported the famous sail were deeply rooted in robust vertebrae, creating a rigid backbone capable of supporting the animal's weight during land-based activities. The zygapophyses, which connect individual vertebrae, were large and well-developed, suggesting that the spine could handle the mechanical stresses of terrestrial locomotion without collapsing. The arms, while shorter than those of typical theropods, were short and robust forelimbs specialized for prey capture rather than swimming paddles, as noted in Sereno News 2022. The shoulder girdle was broad and strong, designed to support arms that could be used for balance during walking or for manipulating prey on land. These terrestrial adaptations paint a picture of an animal that never fully abandoned its theropod heritage. But the most compelling evidence for this dual lifestyle would come from fossil discoveries in places where no swimming dinosaur should ever be found. The discovery that fundamentally challenged the aquatic-only theory came from an unexpected place: Niger's Eulemedon and Chad inland basins, hundreds of miles from any ancient coastline. When paleontologists found Spinosaurus fossils in these inland basins, they faced a problem that nobody could explain away. These weren't isolated bone fragments that might have been transported by rivers or storms. These were substantial remains, including the fossils of Spinosaurus tenerensis, found in geological formations that represented ancient terrestrial environments with no connection to major water bodies. The geological context of these Niger discoveries paints a picture that directly contradicts the idea of a water-bound predator. As documented in Sereno News 2022, the fossil sites contain evidence of terrestrial riverbank deposits, far from any coastline, the kind of sediments left behind when rivers occasionally flood their banks. More importantly, these sites are filled with the remains of terrestrial herbivores, creating an ecosystem that was primarily land-based. This wasn't the environment where you'd expect to find a highly specialized aquatic predator, yet there Spinosaurus was thriving hundreds of miles from any prehistoric marine coastline. This geographical distribution creates a major problem for the fully aquatic interpretation. All secondarily aquatic vertebrates, larger than 6 to 10 feet, evolved their aquatic adaptations only after small-bodied marine origins, as detailed in eLife 2022. Sea turtles, whales, seals, and sirenians followed this evolutionary pathway, developing their water-dwelling capabilities when they were much smaller creatures before increasing in size once fully established in marine environments. The body size issue presents another challenge that researchers couldn't ignore. Spinosaurus aegyptiacus reached massive proportions, and its older relative Spinosaurus tenerensis was equally gigantic. This would represent the only known instance among vertebrates where the evolution of a secondarily aquatic lifestyle occurred at such an enormous body size. Every other large marine vertebrate followed the same evolutionary pathway: ichthyosaurs. Plesiosaurs, mosasaurs, and early whales all developed their aquatic adaptations when they were relatively small creatures. The Niger fossils also revealed something else that didn't fit the aquatic narrative. Spinosaurus fossils are found alongside terrestrial sauropods and theropods in inland fluvial deposits. The fossil assemblages from these sites show a typical Cretaceous terrestrial ecosystem, complete with plant-eating dinosaurs that never ventured near water. If Spinosaurus was truly a water-dependent predator, what was it doing in these inland environments, and how was it surviving without constant access to fish-filled rivers? The answer became increasingly clear as researchers examined the complete fossil record. Spinosaurus wasn't confined to aquatic environments because it wasn't a purely aquatic animal. The inland discoveries revealed a predator that likely frequented both shallow waterways and nearby land for feeding and nesting, supporting a semi-aquatic ambush predator model. These fossils showed that Spinosaurus possessed the mobility and adaptability to hunt across diverse landscapes from riverine environments to inland plains. The evidence pointed to something far more remarkable than anyone had imagined. What we're looking at with Spinosaurus represents an unparalleled blend of land and water adaptations among dinosaurs. This wasn't a crocodile that occasionally wandered onto land, or a land animal that dabbled in fishing. This was a 33,000-pound apex predator, equally comfortable stalking prey through shallow rivers and hunting across inland plains. The combination of aquatic adaptations with retained terrestrial strength created the ultimate opportunistic hunter. This dual adaptation reshapes our view of dinosaur ecology. Specialists may have been rarer than we thought. Maybe other dinosaurs were far more versatile than our simple classifications suggest. Next time you imagine a dinosaur, think beyond land or sea.
For over a century, Triceratops has been the poster child of dinosaurs, that iconic three-horned face adorning museum halls and children's books worldwide. But what if everything we thought we knew about this beloved creature was fundamentally wrong? In 2010, two paleontologists dropped a bombshell that shattered decades of scientific certainty. They claimed that Triceratops, the dinosaur millions of people have grown up loving, might never have existed as a distinct species at all. Instead, it could be nothing more than a teenage version of an entirely different dinosaur.
For decades, paleontology textbooks presented Triceratops and Torosaurus as textbook examples of separate species based on their distinct morphological features. Triceratops has a short, solid frill. Torosaurus has a long frill with holes. The classification seemed straightforward and unquestionable. However, when researchers began examining these skulls under microscopes, histological studies by Horner and Goodwin revealed that the bone tissue in Triceratops' frills remained immature and spongy, exactly what you'd expect in a growing animal. This revelation forced scientists to confront an uncomfortable truth. We might have been misidentifying growth stages as separate species for decades, fundamentally misunderstanding dinosaur diversity. But this discovery was just the beginning of a much larger problem that had been hiding in plain sight throughout the entire history of paleontology. For over a century, paleontologists operated with absolute certainty when classifying ceratopsian dinosaurs, measuring skull dimensions, and documenting frill patterns with meticulous precision. Museums worldwide displayed Triceratops and Torosaurus as distinctly separate species based on clear morphological differences. Triceratops possessed a distinctive short, solid frill, while Torosaurus displayed an elongated frill punctuated by two large openings called fenestrae. Scientists confidently assigned species names based on these morphological markers, never questioning whether they might be observing different life stages of the same animal. The scientific community embraced this classification with remarkable unanimity. Research papers describe the creature's distinct ecological niches, behavioral patterns, and evolutionary relationships without considering ontogenetic variation. This confidence masked a fundamental gap in understanding dinosaur development. Modern reptiles and birds undergo dramatic skeletal changes as they mature, yet paleontologists rarely applied this knowledge to fossil classifications. A juvenile ceratopsian, once named Dracorex, later proved through histology and ontogenetic series to be a young Pachycephalosaurus. The spikes that scientists used to define an entirely new genus were simply immature bone formations that would eventually fuse into the characteristic dome shape of adult skulls. Similar revelations emerged across multiple dinosaur groups, with young ceratopsians displaying wildly different skull proportions compared to their adult forms. The fenestrae in supposed Torosaurus skulls showed signs of active bone growth around their edges, suggesting these openings might represent incomplete development rather than permanent anatomical features. Detailed histological analysis would later reveal the true nature of bone tissue development in these frills, fundamentally changing our understanding of ceratopsian growth patterns. For the Triceratops-Torosaurus synonymy theory to gain acceptance, three critical predictions required validation. First, both forms must occupy identical geographic ranges and time periods. Second, the rarity of supposed Torosaurus specimens must align with natural mortality patterns where few individuals reach full maturity. Third, intermediate forms displaying transitional characteristics must exist in the fossil record. When scientists finally began testing these predictions using advanced analytical techniques, they would face an immediate challenge that could either validate or completely destroy their revolutionary hypothesis. Paleontologists began systematically mapping fossil discoveries across Western North America, creating detailed charts that tracked every specimen from Saskatchewan down to Colorado. This massive undertaking required examining museum collections, field reports, and geological surveys spanning over a century of excavations. Teams spent months cross-referencing fossil locations with precise stratigraphic data to determine exactly when and where each specimen lived. The investigation focused on a narrow but crucial window in Earth's history, the late Maastrichtian period, spanning approximately 68 to 66 million years ago. This time frame represents the final 2 million years before the asteroid impact that ended the age of dinosaurs. Both supposed species appeared exclusively within these rock layers, as documented in the mapped distributions from Longreach, and Field's analysis suggesting they inhabited the same ancient landscapes during this critical period. Expedition teams retraced fossil hunting routes through the Badlands of Montana, Wyoming, and the Dakotas. Researchers retraced field crews' footsteps across the Badlands and found Triceratops and Torosaurus teeth side by side in the same sandstone layers. The Hell Creek Formation in eastern Montana yielded particularly rich evidence containing numerous specimens of both forms preserved in identical sedimentary layers. Similar discoveries emerged from the Lance Formation, Denver Formation, and Scollard Formation, each revealing the same pattern of overlapping distributions. Results from this geographic analysis delivered a shocking revelation. Both forms occupied virtually identical territories across what geologists call Laramidia, the western landmass that existed when North America was split by an inland sea. The creatures roamed the same river plains, forested regions, and coastal environments without any significant geographic separation. This geographic overlap dismantles the idea of two separate species living in different habitats. Separate species typically occupy distinct ecological niches or geographic ranges, preventing direct competition for resources. The complete overlap between Triceratops and Torosaurus territories suggested something far more complex than simple coexistence. The implications extended beyond just these two dinosaurs. If paleontologists had misidentified growth stages as separate species, in this case, how many other supposedly distinct dinosaurs might actually represent different life phases of single species? The geographic evidence strongly supported the synonymy theory, eliminating one major objection to Horner and Scanner's proposal. However, this geographic success only intensified another puzzling aspect of the debate that would prove far more challenging to explain. Museum collections revealed a stark numerical disparity that initially seemed to demolish the synonymy theory. Thousands of Triceratops skulls and skeletal fragments filled storage rooms across North America, making it one of the most abundant dinosaur species in the fossil record. Meanwhile, Torosaurus specimens remained extraordinarily scarce, with fewer than a dozen complete skulls discovered after more than a century of intensive fossil hunting across the same geographic regions. Paleobiological studies show juvenile mortality was high, so adult fossils are naturally rare, consistent with Triceratops reaching Torosaurus stage only in a few individuals. Critics seized on this rarity paradox as definitive proof against the controversial proposal. Research teams argued that if Torosaurus simply represented mature Triceratops, adult specimens should appear more frequently in fossil collections. The logic seemed unassailable. Thousands of juveniles should produce substantial numbers of adults, not just a handful of rare specimens scattered across museum drawers. The scientific community pointed to the complete absence of intermediate forms between supposed juvenile Triceratops and adult Torosaurus as further evidence against synonymy. Critics demanded explanations for why the fossil record would preserve countless young animals, while virtually eliminating evidence of their mature counterparts. Initial histology on a single Torosaurus suggested maturity, but the sample is too small and bone remodeling rates vary, with environment questioning its reliability. The discovery of Nedoceratops hatcheri intensified the controversy by introducing a potential transitional form into the debate. This mysterious specimen possessed a partial opening in its parietal bone, suggesting an intermediate stage between solid Triceratops frills and fully fenestrated Torosaurus skulls. However, Andrew Fark's reanalysis concluded the whole was a healed injury, not a growth stage, removing the supposed intermediate. The rarity paradox actually revealed a fundamental truth about dinosaur mortality patterns. Most individuals in any population die before reaching full maturity, making adult fossils naturally scarce compared to juvenile remains. This biological reality suggested that the abundance disparity between Triceratops and Torosaurus might actually support, rather than contradict, the synonymy theory. Yet this revelation carried implications that extended far beyond just two dinosaur species, threatening to reshape our understanding of prehistoric life itself. The Triceratops-Torosaurus debate underscores how crucial growth stage analysis is to naming species. Paleontologists must test synonymy predictions, shared distribution maturity differences, and intermediates before splitting taxa. Some estimates suggest ceratopsid diversity dropped sharply in the last 2 million years of the Cretaceous, setting the stage for the asteroid's final blow. This controversy exposes a fundamental problem plaguing paleontology for generations. Researchers have consistently misinterpreted ontogenetic changes as evidence of distinct species, artificially inflating diversity estimates across multiple dinosaur groups. The study of dinosaur ontogeny reveals how dramatically these animals transformed from juvenile to adult forms, yet classification systems ignored these developmental patterns when assigning species names. The implications extend far beyond just ceratopsian dinosaurs. Other horned dinosaur classifications now face intense scrutiny, as researchers examine whether additional synonymies exist within established taxonomic groups. Longrich and Field's parsimony-based growth series showed both Triceratops and Torosaurus include immature and mature individuals, contradicting them as separate species. Advanced microscopic analysis techniques are forcing scientists to reconsider decades of accepted classifications. Throughout dinosaur paleontology, bone histology examination allows researchers to assess the relative maturity of fossil specimens by studying their cellular microstructures. These techniques reveal developmental patterns that traditional morphological analysis completely missed, exposing how many supposed species distinctions actually represent different growth stages. The recognition of ontogenetic variation becomes critical for accurately assessing dinosaur diversity and understanding ancient ecosystems. Paleontologists must now consider ontogeny as a source of major morphological variations before naming new dinosaur species, fundamentally changing how the field approaches taxonomic classification. This debate illustrates science's self-correcting nature and relentless pursuit of truth. The controversy continues as researchers present evidence supporting different interpretations of the same fossil specimens. The initial classification of Triceratops and Torosaurus as distinct species seemed logical, based on obvious skull differences. but challenging long-held views forces continuous re-evaluation of existing evidence. The willingness to question even the most established classifications demonstrates something remarkable about how scientific understanding advances through rigorous analysis and open discussion. Bone histology and stratigraphic mapping have rewritten what we thought we knew about Triceratops and Torosaurus, reminding us that even iconic dinosaurs can be reclassified when we apply rigorous ontogenetic analysis. When researchers challenged a century-old classification system, they demonstrated science's willingness to question its most fundamental assumptions. This controversy shows how paleontology advances through continuous re-examination of evidence, even when it means potentially losing one of our most beloved dinosaurs. The three-horned giant we thought we knew might actually represent an adolescent phase of a completely different creature. Which other familiar fossils might turn out to be teens in disguise? Science won't stop asking that question anytime soon. If this sparks your curiosity about dinosaur growth and classification, let us know in the comments which ancient creatures' life stages you'd like to see re-examined.